Welcome back, everyone. Today we step into our third module, shifting our focus from single surface radiative properties to the complex spatial interactions within multi-surface systems. We are going to look deeply at how energy travels through space between distinct bodies, a concept governed entirely by the geometry of view factors. Let's look over our core roadmap to see what we will master by the end of this module.
Our journey through this unit is anchored by 4 primary milestones. First, we will define the purely geometric nature of view factors, exploring why they remain completely independent of any underlying material choices or thermal conditions. Next, we want to develop fundamental relations and analytical shortcuts that make complex systems with multiple interacting surfaces mathematically manageable. Third, we will evaluate self-viewing geometries, learning how to handle the boundary conditions of flat, convex, and concave shapes. Finally, we will pull all these geometric pieces together to apply standard analytical models, calculating the actual net radiation heat transfer between complex three-dimensional surfaces. Mastering these 4 pillars is what allows us to solve actual industrial design and environmental configuration problems. Let's start with our first concept and break down what a view factor truly represents. Fundamentally, a view factor represents the exact fraction of radiation that leaves an initial emitting surface and directly strikes a target receiving surface. As the explanatory notes state on the left half of the slide, this is a purely geometric quantity. It is entirely unaffected by surface properties, material colors, or absolute temperature fields, meaning it is completely decoupled from thermodynamics. Looking right at the center of those notes, the boundary equation defines the physical limits of a view factor, stating that this energy fraction must always fall strictly between 0 and 1. To build a reliable mathematical framework around this, we establish a few core assumptions listed at the bottom. We assume our participating surfaces are completely isothermal, that they act as diffuse emitters and diffuse reflectors, and that they interact across a perfectly non-participating medium. The multi-arrow schematic on the right illustrates this perfectly, showcasing an emitting source distributing its energy fraction across multiple surrounding walls. To understand how we compute these fractions from a fundamental standpoint, we have to look at the calculus of spatial communication. The spatial diagram tracks 2 distinct, arbitrary surfaces separated by space. When tracking the energy exchange between them, we must account for several critical geometric parameters highlighted across the schematic: the total area of both the emitting and receiving surfaces, the specific angles formed between each surface's normal vector and their shared connecting baseline, and the inverse square distance separating them, which naturally dictates how radiative intensity diminishes over space. If you look straight at the bottom of the slide, the primary expression defines the fundamental double integral used to derive a diffuse-to-diffuse view factor between 2 finite areas. It systematically aggregates these individual surface orientations and distance constraints across both participating surfaces. Fortunately, in engineering practice, we rarely have to evaluate this complex double integral from scratch because standard configurations have been pre-solved for us. Let's see how we can evaluate some of these shapes instantly just by observing their curvature. Evaluating surface curvature is one of our fastest analytical shortcuts because it establishes immediate boundary conditions. Let's trace the behavior across our primary geometric panels. In the first panel, we have a flat plane surface. Any radiant ray leaving it shoots straight out into the void and can never turn around to strike itself. Consequently, the equation positioned right below it defines the flat plane boundary condition, setting the self-view factor to exactly 0. Moving to our second panel, bending that surface outward into a convex shape causes the rays to diverge even further into space. Thus, the expression beneath it defines the convex boundary condition, which also equals exactly 0. However, looking at the third panel, when we curve the surface inward to create a concave shape, the surface can now directly see a portion of its own geometry. The relation below it defines this concave boundary condition, establishing that the self-view factor must be greater than 0. Finally, if we shift our perspective to the special case highlighted on the far right, we see a small inner sphere completely enveloped by a larger outer shell. The final equation at the bottom right defines the upper boundary condition for concentric spheres, noting that because the outer shell intercepts all radiation leaving the inner core, that view factor equals exactly 1. For common engineering configurations, we can completely bypass double integration by utilizing a pre-compiled catalog of analytical standard models. As the opening text highlights, these models reduce complex spatial integrals to standard, manageable algebraic formulas based on dimensionless geometric ratios. Tracing our rows from top to bottom, we can see how this catalog is organized. The top row illustrates 2 aligned parallel plates, where the algebraic solution is defined cleanly by dimensionless parameters of length and width, normalized by the separation distance. The middle row details 2 parallel coaxial disks, where the system is defined by normalized ratios of the individual disk radii. The bottom row maps out two perpendicular plates sharing a common edge, where the equations rely on ratios of height and width normalized against the shared base length. When you tackle multi-surface design problems, your very first step will always be calculating these simple dimensionless parameters so you can use these solved equations. To streamline our design workflows even further, these complex algebraic relations are often plotted directly onto standard design charts. This specific chart provides a fast graphical solution for parallel coaxial disks. Following the operational notes outlined on the right, we can easily master the reading process. In step 1, you compute your specific disk spacing ratio and locate it along the logarithmic horizontal axis. In step 2, you track that value straight up vertically until you intersect the specific parametric curve representing your disk ratio. In step 3, you read horizontally across to the linear vertical axis to find your final view factor. Now, let's look at the critical physical behavior highlighted at the bottom right of our chart. As the separation distance between the two disks approaches 0, they move so close together that they effectively form a perfect enclosure. The note positioned at the bottom right defines this limit, stating that the view factor for equal-sized coaxial disks rapidly approaches an absolute value of 1.0 under these tightly coupled conditions. When working with multiple surfaces, the total number of view factors you must track grows quadratically as the square of the surface count. To prevent this from becoming mathematically overwhelming, we rely on a powerful analytical toolkit consisting of 4 foundational geometric rules. Let's preview how this matrix is structured before we see them in action. The top left quadrant defines the reciprocity relation, which allows us to find a reverse view factor from a known area pair. The top right quadrant defines the summation rule, used to compute a final unknown factor within any completely closed enclosure. The bottom left quadrant defines the superposition rule, which lets us break down large, complex composite surfaces into basic, easily solvable geometries. Finally, the bottom right quadrant defines the symmetry rule, allowing us to immediately have our calculation requirements in mirrored spatial layouts. Let's look closely at how these rules function mechanically. Let's take a closer look at the exact mechanics driving our first 2 foundational tools. The equation spanning across the top half of the slide defines the reciprocity relation, which directly balances participating surface areas against their respective view factors. As the accompanying text explains, this tool allows us to calculate an unknown view factor using our knowledge of its reverse direction. This is absolutely critical when you are evaluating radiation moving from very small emitting surfaces into vast, sprawling receiving spaces. Moving down to our second tool, the formula centered on the lower half defines the summation rule for closed enclosures. Because energy must be conserved, any radiation leaving a surface inside a completely closed enclosure must be entirely intercepted by the walls of that enclosure. For a system with an arbitrary number of surfaces, this conservation law acts as an incredible analytical shortcut. It ensures that engineers only need to independently calculate a limited fraction of the total factors, with the enclosure equations effortlessly filling in the final unknown values. Let's examine the remaining 2 rules in our toolkit, which deal with complex shapes and repeated patterns. The top graphic illustrates a single baseline surface interacting with a complex composite surface that is broken up into individual segments. The equation positioned next to this diagram defines the superposition rule, stating that the total view factor from a base surface to a composite surface is simply equal to the algebraic sum of the individual view factors to its constituent parts. Shifting our perspective to the lower half of the slide, we see an observing surface looking at 2 separate, perfectly mirrored curved panels. The formula accompanying this layout defines our symmetry relation. This rule dictates that if 2 or more target surfaces possess perfect geometric symmetry relative to a third observing surface, they must receive an identical fraction of energy. This gives you an instant shorthand to copy known view factors without repeating calculations. When you are working with long industrial channels or air ducts where the geometry is essentially infinite relative to its cross-section, we can bypass 3-dimensional space entirely using a classic method called the cross-strings algorithm. The schematic on the left displays 2 opposing arbitrary surfaces with distinct endpoints. Following the 3-step workflow outlined on the right, we can solve this using imaginary strings. In step 1, we draw uncrossed strings connecting the outer endpoints of the 2 surfaces. In step 2, we draw diagonally crossed strings connecting the opposing endpoints. Finally, in step 3, we apply our governing algebraic relation. The equation structured at the bottom right defines Hottel's cross strings relation, stating that the view factor is equal to the sum of the cross strings minus the sum of the uncrossed strings, divided by 2 times the total length of the emitting surface. It is a brilliant geometric shortcut that completely avoids calculus, allowing you to solve complex, infinitely long two-dimensional shapes using simple line lengths. Now, let's synthesize our geometric view factors directly into a complete thermal energy equation. The central formula on this slide defines the net radiation heat transfer between two ideal black surfaces. Notice how this master expression perfectly decouples the problem into two entirely separate physical blocks via our structural callouts. The first callout on the left defines the spatial geometry block, which is the precise view factor we calculate using our integrals, standard catalogs, or the crossed strings method. The second callout on the right defines the thermodynamic driver block, representing the net emissive power differential governed strictly by absolute temperatures and the Stefan-Boltzmann law. As the final text at the bottom summarizes, by assuming ideal black surfaces with zero reflection, the entire net heat transfer problem simplifies beautifully into a direct product of spatial view geometry and pure temperature differentials. Keep in mind that if your final solution yields a negative value, it simply indicates that net heat is physically flowing backwards from the second surface to the first. To help you approach multi-surface problems methodically, this flowchart maps out a standard 4-stage enclosure analysis workflow. Walking through the steps from left to right, we begin with Stage 1, where we define our geometry by classifying the space as a finite 3-dimensional enclosure or an infinite 2-dimensional channel, while pinning down any self-viewing boundary conditions. In Stage 2, we look up our primary relations, pulling standard algebraic equations from 3-dimensional catalogs, or setting up string lengths for 2-dimensional configurations. In Stage 3, we exhaust our analytical shortcuts, using reciprocity for reverse factors, symmetry for mirrored layouts, and summation rules to solve for the final remaining unknowns. This brings us to Stage 4, highlighted in bright pink, which defines our final thermal synthesis step. This is where we combine our fully solved geometric view factor matrix with our absolute thermodynamic emissive power limits to calculate the final net heat transfer rate. Following this workflow step by step prevents you from getting lost in multi-surface problems. To wrap up our discussion on view factor geometry, let's consolidate our core foundational principles into 4 key takeaways. First, always remember that geometry comes first. View factors are purely geometric quantities that depend solely on spatial orientation and distance, remaining completely independent of material surface properties or temperature limits. Second, master your summation laws. For any closed enclosure, the sum of all view factors leaving a surface must equal unity, giving you a powerful conservation tool to simplify your calculations. Third, analyze your self-viewing boundaries. Surface curvature completely dictates self-views, meaning concave surfaces can see themselves, while flat and convex shapes do not. Finally, embrace 3D modeling. Standard analytical catalogs and numerical integrations are what allow us to perform precise heat transfer analysis between intricate 3-dimensional engineering structures. Never treat layout as a minor detail. It is the physical pipeline of radiative exchange. That concludes our deep dive into the geometry of view factors. I want to leave you today with the foundational principle displayed at the bottom of our final slide. Heat transfer is a study of the exchange of thermal energy, which occurs whenever there is a temperature difference. View factors act as the spatial gateways of that exchange, mapping out exactly how energy flows across space from source to destination. Thank you all for your excellent focus and active participation today.